Welcome dear students, welcome to today's online class. Today we discuss the second type of molecular spectroscopy in detail, that is UV visible or electronic spectroscopy. In the introductory classes we have seen that in a molecule, when electronic transition takes place from lower electronic level to higher electronic level, the radiation absorbed is from UV visible region of electromagnetic spectrum. That is why these synonyms. Electronic spectroscopy is also called UV visible spectroscopy. Today we discuss the first part of UV visible spectroscopy. We discuss three things. Number one, the range of UV visible radiation used for the study, and then a very important underlying law in connection with this electronic spectroscopy, that's called Beer-Lambert's law. And also we discuss various types of electronic transitions which takes place in molecules. First of all, range of study. See, in electromagnetic spectrum, if we check the wavelength of ultraviolet as well as visible radiation, it ranges from 10 nanometer to 200, then 400 up to roughly 800 nanometer. Let me divide these things. Here, you know that this is 400 to 800 nanometer wavelength correspond to which one? Visible region, right? And this much correspond to UV, ultraviolet, which can be divided into two types. Below 200 is called far UV or vacuum UV, far or vacuum UV, and this is near UV. Okay. So near in the sense near to the visible range, far from visible range. Why this below 200 is known as vacuum UV? It is because most of the air molecules like N2, O2, etc. absorb below 200 nanometer for their electronic transition. Remember, in electronic spectroscopy, the selection rule is that all molecules are having electronic spectroscopy or they can absorb UV visible radiation, unlike IR spectroscopy, which we discussed in the previous classes, where the selection rule or the necessary and sufficient condition for a molecule to be IR active is what? That during vibration there should be change in dipole moment for an electric pulse to be generated so that it can interact with the radiation. But in electronic spectroscopy or UV visible spectroscopy, there is no such condition. That means all molecules are able to absorb UV visible radiation. It is because during electronic transition, see, you know that movement of electron itself create an electric pulse, right? Therefore, in every electronic transition, there will be an electricity produced or electric pulse generated so that molecule can absorb UV visible radiation. Now, so in molecules in air like N2, O2, etc. are found to absorb below 200 nanometer, right? So, if you have a molecule which is taken for this study and it is having an absorption below 200, then you need to evacuate the instrument. The UV visible spectrometer is to be evacuated to take the UV visible spectrum, electronic spectrum of your molecule, because otherwise the air molecules will interfere, right? Because they also absorb below 200. So to study molecules having absorption below 200, you need an evacuated UV visible spectrometer. That's why this region is known as vacuum UV. Okay. Because of that, below 200 is of little interest for spectroscopists. So mostly the study is from 200 to 800, this near UV as well as visible range. Now coming to the next one, there is an important law in connection with UV visible spectroscopy, that is Beer-Lambert's law. Beer-Lambert's law. Now this law is talking about the absorption of light. This is about absorption of radiation, absorption of light in general. Let's consider a case. See, we have an absorbing medium here, say for example a solution which contains some molecules which can absorb UV visible radiation, and we are sending a monochromatic radiation from UV visible range having an intensity I0, the intensity of the incident radiation. See, the molecules in the solution will absorb part of the radiation so that the intensity of the transmitted radiation will be less. Let's try it is Ix, and I am marking here this length of the solution, thickness of the solution is X. And also, suppose the solution taken here has a concentration of C moles per liter, molar concentration. What does this law says? Beer-Lambert's law says that when a monochromatic radiation is passed through an absorbing medium, the rate of decrease in intensity, the rate of decrease in intensity of the radiation with thickness of the solution is directly proportional to the intensity of the incident radiation as well as concentration of the solution. So this is the law in short. You have to remember this point. When a monochromatic radiation passes through an absorbing medium, I told you that the intensity will fall. So that rate of decrease in intensity with thickness, of course it varies with thickness. If there is more length of solution, more molecules will be there, there will be more decrease in intensity. So that is proportional to two things, intensity of the incident radiation as well as the concentration of the solution. More the concentration, more will be molecules and more will be decrease in intensity. This can be mathematically written as minus di by dx proportional to intensity of the radiation as well as concentration. Equating, we write a proportionality constant k into IC, where k is constant of proportionality, which depends on two things. One is the nature of the radiation used, second the medium, the absorbing medium. Of course, this is a differential form. Better we will integrate and get a better solution equation, for which we make some rearrangements, like I is taken to this side, so di by I is equal to minus taken to that side minus k c dx. Integrating between the limits, here the limit for intensity will be I0 to Ix, right? And for x it is x equals 0 to x. So what do you get? Let's write the equation now. we'll get it as this log, the di by integral is log I, okay, between the limits I0 to Ix equal, here the constants k and c, and x is, you get x dx, integral of dx is x, between the limit 0 to x. So what you get here? You get it as log Ix minus log I0 will be what? Log Ix by I0 equal minus kc x minus 0, it become kcx. Right? Now, we can take this negative to this side and take the reciprocal. What do you get? Log I0 by Ix is equal to kcx. We know that mostly we represent this in common logarithm, multiplying by 2.303 here and taking to the other side. You can write the equation now. Log I0 by Ix equal, you get, it will be k by 2.303 cx, and this is another constant, what is written as epsilon cx. So the equation is log I0 by Ix is equal to epsilon cx, where epsilon is called molar absorption coefficient. Molar absorption coefficient is a constant, or molar extinction coefficient, or also called molar absorptivity. Now this log I0 by Ix is again replaced by another term, that is capital A epsilon cx. This will be the most simple form of mathematical expression of Beer-Lambert's to remember, that is A is equal to epsilon cx, where A is defined as, it is log I0 by Ix, that is known as absorbance. That is absorbance. How far the absorption takes place in logarithmic term. It's also called optical density. Right? This is a very important term related to electron spectroscopy, that is absorbance. So this is Beer-Lambert's law. Now finally, we have to define this constant molar absorption coefficient. For that purpose, what we do is, for making a definition, we will write it like this. Here from this we can get epsilon is equal to what? 1 by cx log I0 by Ix, right? This is molar absorption coefficient. Remember, what is the unit of epsilon? This has no unit. Concentration in moles per liter, and X thickness is taken in centimeter in this purpose. So the unit of epsilon will be what? Taking the reciprocal will be liter mole inverse, right? And centimeter inverse will be the unit. Now coming to the definition of epsilon, what we do is, we have to make this as unity 1, for which, let's take Ix is equal to I0 by 10. So what do you get? When Ix is replaced by I0 by 10, I0 get cancelled, it becomes log 10, which is 1. So that this will become epsilon equal 1 by Cx. Also we take C is equal to 1 molar. In this case, epsilon becomes 1 by X, isn't it? You understand? See, if you replace this by I0 by 10, it becomes log 10 and 1. And C is also 1, so you get this. So from this condition, what is molar absorption coefficient defined as? It is the reciprocal of the thickness of a solution. Of what solution? Of a 1 molar solution, which reduces the intensity of the incident radiation to 1/10 of the value. Because Ix become I0 by 10. That means intensity is reduced to 1/10 of the original value. So I repeat, molar absorption coefficient is defined as the reciprocal of the thickness of a 1 molar solution, which reduces the intensity of the incident radiation to 1/10 of the original value. Okay, so that's about this Beer-Lambert's law, right? This law is made use of in the application part. We will see that later. There are so many applications for UV visible spectroscopy. One is based on this equation, what is known as spectrophotometry. Okay, coming to the last one. In electronic spectroscopy, we know that in molecules, electrons in various molecular orbitals undergo transition from lower level to higher level. What are the different types of electronic transitions possible in a molecule? That can be seen from this diagram. This is the energy diagram. According to MOT, molecular orbital theory, you know that there are different types of molecular orbitals, bonding as well as anti-bonding orbitals, and also there is sigma molecular orbital as well as pi molecular orbitals. So taking all together, we can represent various molecular orbitals in a molecule like this. This is N. I will tell you what is N. This is pi molecular orbital. This is sigma. These are bonding molecular orbitals or BMO. Where sigma, you know, when you discuss the MOT, you might have drawn the molecular orbital energy level diagrams, like sigma 1 is sigma star pi, like that. So it goes like this. Sigma bonding MO is having lowest energy, most stable. Then pi. What is N? N is non-bonding. That is, you can see in some molecules there are lone pairs which are not part of the bonds. They remain in what are called non-bonding orbitals, which are not taking part in LCA or combination. So the lone pairs, non-bonding electrons, and then antibonding orbitals will be this is pi star and this is sigma star, which are the anti-bonding molecular orbital. Okay, now showing various transitions. See, the selection rule is that always electronic transition takes place from either bonding or non-bonding orbitals to anti-bonding. That is the thing. So the transition having maximum energy gap is which one? From sigma to sigma star, he is having maximum energy gap. Okay. Then comes sigma to pi star, pi to sigma star. See, these three transitions we can mark it here. This is sigma to sigma star. This is sigma to pi star transition. This is pi to sigma star transition. These are all having comparatively high energy, and that comes in below 200 nanometers. Remember, lower the wavelength, greater the energy. So in the UV visible range, the part of the radiation having maximum energy is below 200. When it goes to near UV and visible region, energy decreases. Remember that. So these transitions require absorption of UV radiation in below 200, that is vacuum UV. Because of that, this is of less interest. I have told you the reason. Because this is vacuum UV. You need an evacuated spectrophotometer. So this is of less interest. Coming to the remaining transitions. Now what are left out? Next possibility is from, I am writing it somewhere here, N to sigma star, okay, then pi to pi star, and finally N to pi star. Okay, so let us note it. This is n to sigma star. This is pi to pi star, and this is n to pi star. Okay, so these are various transitions. These transitions of course require comparatively lower energy, and it definitely comes above 200 nanometer. That means it may go beyond 200 nanometer, it can go to 400, it can enter into the visible range. So these transitions are more important in electron spectroscopy. So writing all the transitions according to the energy order, maximum energy is for sigma to sigma star, right? Decreases to, these two are roughly same, sigma to pi star nearly equal to pi to sigma star, decreases to, then comes n to sigma star, decreases to pi star, and finally n to pi star. So a question to you, which is a transition having maximum energy, which require maximum energy? Sigma to sigma star. Which having minimum energy? N to pi star. Okay. Now in the transitions, we can see two types of transition. One is called allowed transitions. Another selection rule which comes in electronic spectroscopy is that transition takes place between orbitals having similar symmetry. So here, if you take sigma to sigma star as well as pi to pi star, these two transitions are called allowed transition or symmetry allowed transition, because both orbitals are of same symmetry. And such transitions are more intense. As we have seen, these transitions are of less interest because it comes below 200 generally. So this is an important transition, pi to pi star, which is symmetry allowed, because so that it will be very intense also. Then the second type of transition is called forbidden transition. Forbidden means it is symmetry forbidden. All other transitions are forbidden. So important transitions here like n to sigma star, n to sigma star. Similarly, n to pi star, these are symmetry forbidden because they have different symmetry for the orbitals, of which this is more important, n to pi star. Forbidden transitions will be very weak. The intensity will be lower than that of allowed.